Okay, we're going to be talking for the next 2 days, today and Monday, about average rates of change and instantaneous rates of change. And I want to take a moment to remind you of what those things are. Consider f of x equals x squared. Like so. And if I ask you, what is the average rate of change of f on the interval 0 to 3, like so, then what I'm asking for is the change in f over the change in x. That is, f of 3 minus f of 0 over 3 minus 0. And this computes the average rate of change, and we call this quantity right here the difference quotient. And it is computing the slope of the line that connects the 2 points from x equals 0 to x equals 3. And we call this line a secant line because it cuts through the curve at these 2 points. So an average rate of change is a difference quotient. It is a slope of a secant line. And in fact, when I do this computation for this particular function on this particular interval, I get 3. Like so. Now, if I ask a different question, what is the instantaneous rate of change of f at x equals 2? I want to answer this question in a related but different manner, because an instantaneous rate of change is another word for a derivative. That's right. So I would spell this answer as f prime of 2. And if I wanted to, I could write that as the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 all over delta x. There's my definition of the derivative that computes that for me. It is the limit of a difference quotient. But I have so many derivative rules that I can simply use those derivative rules to immediately get the instantaneous rate of change. You've probably done it in your head already. What is it? Yeah, it's 4. Because f is x squared, f prime is 2x, right? F prime of 2 is equal to 4. So although I can compute the derivative as the limit of a difference quotient, I don't usually, unless I have to. So I want to point out the differences between the language and the concept. The instantaneous rate of change is going to be the slope of the tangent line. And you can see that this tangent line is somewhat steeper than this secant line right here. The first difference is just the language, average versus instantaneous. The second difference is the specification. An average is taken over an interval, whereas an instantaneous rate of change, understandably, is evaluated at a point, at an instant. And then next is the computation. The difference quotient, delta f over delta x, computes an average rate of change, and the limit of that difference quotient computes an instantaneous rate of change. Specifically, the limit as the denominator goes to 0. Does this make sense to everybody? Now the big question. Suppose I give you a function and I tell you some things about its instantaneous rate of change. Can you figure out some things about its average rate of change from that information? Or vice versa. Suppose I tell you something about the average rates of change. Can you figure something out about instantaneous rates of change? Maybe so. And that's really what we're going to explore over the next 2 days. But to get there, today we're going to focus on just one theorem, which is Rolles' theorem. So the big question that we're trying to answer is there a deep relationship between the information that we get from delta f over delta x, the average rate of change, and instantaneous rate of change f prime of x. Okay, well, we're going to get there in stages. As I said, we're going to start with Rolles' theorem. So what we're going to do here is I'm going to ask you to draw a function that has several conditions imposed upon it. And the first condition that I'm going to ask you to impose, go ahead and set up coordinate axes and pick an A and a B. My A and my B are going to be right here, but you can pick yours anywhere you want on the x-axis.
Can I be negative?
Sure. Is that part of anywhere? All right. Now, here's the first condition I want you to impose. I want you to pick a value for f of A and f of B and make it the same value. So our first condition is that I want f of A to equal f of B. Now, for the second condition, actually I'm going to ask you for the second and third conditions together. I'm going to ask you to draw a function between A and B so that your function is continuous and differentiable. Continuous, pretty clear. Differentiable, no corners, no cusps, no vertical tangents. Okay? Go ahead. Draw a function, any function, between f of A and f of B that is both continuous and differentiable. It can look like anything as long as it's continuous and differentiable. That works. Yep. That works. Good. Okay, that works. And that works. Good. Got some different things here. I'm going to draw one. Here, here's mine. Okay. Now, it turns out, for the purposes of Rolles' theorem, that we can actually leave out the endpoints for differentiability. So, as far as conditions that we're going to impose on our function, the conditions are going to be that f of A equals f of B, f is continuous on the closed interval A to B, and f is differentiable on the open interval A to B. If these things are true, then, question, can you find a point on your graph where f prime is equal to 0? If so, draw a horizontal tangent at that point.
Point or point?
Yeah? You could have more than one, just at least one. Here's one of mine. And I actually have several points where f f prime is equal to 0. I'm going to call that C. And what I observe is that C lives between A and B. Rolles' theorem actually guarantees that there must be such a C if the conditions that I mentioned are met. And looking around, sure enough, all of you have found at least one C. Tony has an infinite number of C's.
Yeah.
It's either a constant function, right? So that if these three conditions are met, then there is a C in AB such that f prime of C is equal to 0. Now, first we want to tackle why is this true, and then we would like to come back and show exactly how do we use this, or is this good for? Okay, why is this true? Why is it not an accident that I was able to guarantee without any hesitation that all of you would be able to draw a function, would necessarily draw a function that had a point of horizontal tangency?
Because after A and F and B are the same, so it is increasing, then it has to come back down. So the person has to come back down.
Okay, and so if it's increasing and then has to come back down, or decreasing,
It's local max or a local vector max.
you got it. That's the spirit of the proof. That's exactly it. So here's our proof. Very good. First of all, are we guaranteed that our function has a max and a min? Yes. Which condition guarantees that? No.
Just continue.
It's continuous on the closing bounded interval. What theorem was that? Just gonna look it up. Now, I had to fuss at my other class. You guys want to know the names of your theorems because it gives you useful handles to talk about this stuff. Since f is continuous on AB, f has a max and a min. And what is the name of that theorem? Ah! What did you say? It is called the extreme value theorem. It is a lot easier to learn proofs, to learn theorems if you learn their names with them. You don't want to learn the text and not have a handle. Okay? So that's the extreme value theorem. So it has a max and it has a min. Now, where are those maxes and mins located? You mentioned local max, but these are actually absolute maxes and mins. To be a local max, it has to be a max on the open interval A to B. So that's one possibility. Absolute extrema can occur at the interior, but they can also occur where? The endpoints. So we really have a couple possibilities. One possibility is that both of my max and min occur at the endpoints. And the other possibility is that one of them or both of them occur in the interior. There are only two possibilities.
If the max and min are both at endpoints, is that one?
Ah, very good. Possibility number one. If the f max and the f min are both at endpoints, then that means that they have to be equal to f of A and f of B. But f of A equals f of B. And so because f of a equals f of b, f max equals f min, there is only one kind of function whose max is equal to its min, and that's a constant function. That's exactly right. The logic here is very similar to the squeeze theorem. If f is always between its max and its min, and if those two are equal, then f is always equal to the constant value. Okay? Well, if f is constant, then what is f prime? 0 for every value of x. So there are an infinite number of c's such that f prime of c is equal to 0. So in that possibility, or that case, usually professional mathematicians call these cases, then we have found not just one, but an infinite number of c's such that f prime of c is equal to 0. All right? Possibility number 2. The logical opposite, case number 2. The logical opposite of the statement max and min are both at the endpoints is that one of them is not at the endpoint. Could be both, but at least one of them is not at an endpoint. F max or F min is located somewhere in the interior of A to B. But if that is the case, then we have a local extremum. And we know something about local extrema from Fermat's theorem. Local extrema only occur at critical points. Exactly. So that means that x equals c, the location of the max or min that is at the interior, is a critical point. But now we have an interesting thing, because critical points come in two flavors. Either f prime of c. No, not all critical points.
Critical points.
F prime of c is equal to
0,
or does not exist. However, we stipulated as a condition on our function that f was going to be differentiable on AB, which means it's not possible for f prime to not exist, because that's the opposite of being differentiable. So that means that, therefore, by elimination, f prime of c has to be equal to 0. So this proof is really like a forensic investigation almost. We went through and we eliminated possibilities, took care of them. Possibility number 1, maybe both the max and the min occur at the endpoints, in which case my function has to be constant. Possibility number 2, the max or the min occurs somewhere other than the endpoint, in which case it is local, in which case it must be a point of horizontal tangency. I want you to notice how the three conditions were used here. First, we used continuity to establish that there must be max and min. Then we used the fact that f of A equals f of B to handle the case where the max and min were at the endpoints. And then we used the fact that f is differentiable to handle the case where max or min is in the interior. So all three conditions are necessary, and together they are sufficient to guarantee a point of horizontal tangency. Now, how do we actually use this? What Rolles' theorem is good for is to give us a guarantee of horizontal tangency. So we would use it like this. We would have a given function, we would have a given interval, And now we would ask, on this interval, are we guaranteed a point of horizontal tendency? Now, in this particular case, the function I chose here, the easiest way to find that out is to actually go look for it, right? But, under many circumstances, I don't have enough information, or my algebra is not powerful enough to actually find points of horizontal tendency. I don't necessarily have to be able to find them to say that they're there. And sometimes it's useful just to know that there is a point of horizontal tendency without necessarily knowing where it is. And we'll see that on Monday. That's going to be useful for us on Monday. So, does Rolles' theorem apply on 0 to 3? Well, it's a simple matter of checking our three conditions. So to remind ourselves of our three conditions. Does f of A equal f of B? That's our first condition. Let's check that. What is f of 0 equal to? What is f of 3 equal to? So our first condition is satisfied. Second condition, is f continuous on the closed interval 0 to 3? I'm getting a big head nod. Tell me why. How do you know? Okay, but that's only 0. What about all the x's between 0 and 3? There's an infinite number. Could you generalize that? Is it true in general that the limit as x goes to c of f of x equals f of c? Yeah, it is. That's right. Because we actually have a theorem about a particular type of function. What type of function is this? It's a polynomial, that's right. And our polynomial theorem is that all polynomials are continuous. That the limit as x goes to c of the polynomial equals p of c. So, it is continuous because it is a polynomial. And the third condition is f differentiable on the open interval a to b. And we can also check this by appealing to the fact that f is a polynomial. Or, if you're not really sure, you can actually compute f prime. And f prime here is equal to 2x minus 3. And we ask this simple question, does this f prime exist, have a value for every x in the interval 0 to 3? The open interval 0 to 3. And the answer is yes, it does. And so since my function is continuous and differentiable, and since f of 0 is equal to f of 3, I've satisfied all three conditions, and therefore I conclude that Rolles' theorem applies. Well, how do I apply it? It's actually fairly simple. Now I go horizontal tangent hunting. And to do that, I'm going to set f prime of c equal to 0. And f prime of c is equal to 2c minus 3. And I get the value c is equal to 3 halves. It shouldn't be too surprising to you that when I graph f of x, because my graph is the graph of a quadratic parabola, that the value of c that I got was located halfway between the two zeros. That works for quadratic parabolas, not for every function. How we doing? Now, I want to consider a couple of other possible functions here. Does Rolles' theorem apply to f of x equals, let's make it g of x, since that f was a different function. Equals the absolute value of x. Does Raleigh's theorem apply on the interval -2 to 2? Well, let's walk through and check. First condition. Does g of -2 equal g of 2? Yes. What value do they both have? 2. Is g continuous on the interval -2 to 2? If you're not sure, think about the graph. Can you draw that graph without looking at your pencil? Yep. Is g differentiable on the open interval -2 to 2? No! It has one single point of non-differentiability, and x equals 0. It has a sharp corner right there. G prime of 0 does not exist. And all it takes is one single point of non-differentiability to wreck everything. Because G fails to be differentiable, there is no guarantee of a value of C of such that G has a horizontal tangent. And in fact, for this particular function, it turns out there is not a horizontal tangent anywhere. Okay. So there is no guarantee from Raleigh, because Raleigh's theorem does not apply to this function.
So for this kind of thing, just end here.
In the theorem, you'd say there's no guarantee. Could there be a horizontal tangent for a particular function? Yes, there could be. So the guarantee is not double-sided. If Raleigh's theorem fails to apply, that does not guarantee a lack of horizontal tangency. It only says we don't have a guarantee of horizontal tangency. All right. Well, what if I changed it a little bit? What if I adjusted my interval so that it did not include 0? Maybe I could ask, does Raleigh's theorem apply maybe on the interval 0 to 2? So, but now when I do that, in adjusting my interval, I have to go back and check the very first condition again. Does g of 0 equal g of 2? No. I'm done. If I fail at one condition, Raleigh's theorem does not apply. Finally, let's consider h of x equals root x minus x on the interval 0 to 1. Does Raleigh's theorem apply? Well, let's go checking. Does h of 0 equal h of 1? Yep. What do they both equal? 0. Yep. Is h continuous on the closed interval 0 to 1? And one way to think about this is to consider each of the terms separately. Is the square root of x a continuous function on 0 to 1? Yep. Is x, so therefore the difference of the two continuous functions is also continuous. Yep. Is h differentiable on 0 to 1? Well, to find out, let's actually compute h prime and see what we see. Are there any values of x for which h prime does not exist? What's that? 4?
No.
What? Huh? Why would h prime of 1 over 4 not exist? Is there a problem with the square root of 1/4 that I don't know about? He's not at school. Yeah, x equals 0 is a big problem. because 1 divided by 0, any other values of x that are illegal? Can't think of any values of x that cause problems for square root. Negative values, that's right. So this fails to exist for x's that are less than or equal to 0. But, guess what? I only require differentiability on the open interval 0 to 1. I do not need differentiability at x equals 0. It's okay for me to have a vertical tangent at x equals 0. So therefore, this condition is just barely met. So if I now want to find the guaranteed point of horizontal tangency, I can go hunting for it. H prime of c is 1 over 2 root c minus 1. Set that equal to 0 to find horizontal tangents. Add 1 to both sides. Flip both sides. Divide both sides by 2. And square both sides. We graph this function between 0 and 1. You can see that it has a horizontal tangent right there at x equals 1. How are we doing? Does this make sense to everybody? Okay. Well, where we're going with this is that on Monday we're going to take this entire idea of horizontal tangent hunting and we're going to put it on an angle and tilt it so that instead of hunting for horizontal tangents, we're going to hunt for tangents that are parallel to secants. But that is another theorem for another day.